Welcome back. In the spinal eigenvalue episode, we cache in everything: powers, eigenvectors, diagonalization on a single spectacular application. The setting is a Markov chain, a system that hops at random between a set of states where the next hop depends only on where you are right now. We pack the hop probabilities into a special matrix, apply it over and over, and watch the long run unfold. The headline result is that most such systems forget where they started and settle into one fixed distribution called the steady state, and that steady state is simply the eigenvector for eigenvalue-one. Diagonalization will explain exactly why everything else fades away, and then we will meet the most famous Markov chain ever built, the one Google used to rank the entire World Wide Web, called PageRank. Let's build the setup. We have a system that is always in one of n states. Instead of tracking exactly which state, we track the probabilities, packed into a probability vector, a list of non-negative numbers that sum to 1, where each entry is the chance of being in that state. The defining feature of a Markov chain is the Markov property. The next state depends only on the current state, not on the entire history of how you got there. We say the process is memoryless. All the dynamics live in a transition matrix, which we call P. The entry in row I, column J, is the probability of moving from state J to state I. With that convention, advancing one step is just one matrix multiplication. The new distribution is P times the old one. And advancing k steps means applying pk times, which is p to the k times the starting distribution. So the future of the chain is entirely a story about powers of a matrix, exactly what diagonalization was built to handle. The transition matrix is not just any matrix, it is stochastic, and that structure is everything. A matrix is column stochastic when all its entries are non-negative and every column sums to 1. The meaning is simple: pick any starting state J. The entries in column J are the probabilities of where you go next, and those probabilities have to add up to 1 because you must land somewhere. The crucial consequence is conservation of probability. If you feed in a valid probability distribution, non-negative entries summing to 1, then P spits out another valid probability distribution. Total probability stays exactly 1 at every single step. The chain never leaks or creates probability, it only redistributes it. For instance, the 2x2 matrix with columns 0.9 over 0.1 and 0.5 over 0.5 is stochastic. Each column sums to 1. That conservation property is what forces the matrix to have a very special eigenvalue, as we will see next. Here is the central theorem, and it falls right out of the column sum structure. Every stochastic matrix has the number 1 as an eigenvalue. Here's the quick reason. Saying the columns of P sum to 1 is the same as saying the rows of P transpose sum to 1, but a matrix whose rows each sum to 1 multiplied by the all ones vector just returns the all ones vector. So the all ones vector is an eigenvector of P transpose with eigenvalue 1, and a matrix and its transpose always share the same eigenvalues because they have the same characteristic polynomial. Therefore, P itself has eigenvalue 1. The eigenvector of P belonging to eigenvalue 1, rescaled so its entries are non-negative and sum to 1, is the steady state distribution, which we write as pi. By definition, P times pi equals pi. Applying the transition matrix leaves this distribution completely unchanged. The chain has reached equilibrium. The proportions in each state stop moving, even though individual hops keep happening underneath. Let's look at the whole spectrum of a stochastic matrix, because it explains both whether and how fast the chain settles. 3 facts. First, 1 is always an eigenvalue, as we proved. Second, every eigenvalue has magnitude at most, 1. None can exceed 1 in size, which makes sense because the matrix never grows total probability. So 1 is a dominant eigenvalue, nothing blows up. Third, for a regular chain, one where some power of the matrix has all strictly positive entries, meaning you can eventually get from anywhere to anywhere. The value 1 is the only eigenvalue of size 1, and it is simple, appearing just once. That guarantees a unique steady state. There is a bonus. The second largest eigenvalue in magnitude controls the speed of convergence. The chain settles at a rate governed by that number raised to the k. The gap between 1 and the next eigenvalue is called the spectral gap, and a big gap means fast mixing. Why does the chain converge, and why does it forget where it began? Diagonalization makes it transparent. Write the transition matrix as S times D times S inverse, and express the starting distribution as a combination of eigenvectors, some amount of the steady state pi, plus amounts of the other eigenvectors. Now apply P to the kth power. Each eigenvector piece gets multiplied by its eigenvalue raised to the k. The steady state piece is multiplied by 1 to the k, which is just 1, it never changes. But for a well-behaved, so-called regular chain, every other eigenvalue has magnitude strictly less than 1. And a number smaller than 1 in magnitude, raised to higher and higher powers, shrinks to 0, so every term except the steady state decays away. As k grows, p to the k times the start converges to that one steady state vector, and the coefficient works out so the limit is exactly pi, with no trace of the starting distribution left. The long run is pure steady state. Here is a Markov chain drawn the way people usually picture one, as a diagram. 3 states drawn as circles and labeled A, B, and C. The arrows between them are the possible transitions, and each arrow carries a number, the probability of taking that hop. The one rule you must respect is that the probabilities on all the arrows leaving any single state add up to 1, because from that state you have to go somewhere on the next step, possibly even looping back to yourself. Now look beside the diagram at the matrix. It holds exactly the same information. Each column of the matrix corresponds to one starting state, and its entries are the probabilities of going to each of the 3 states. Because the out arrows from each state sum to 1, each column of the matrix sums to 1, there is the stochastic property made visible. The diagram and the matrix are 2 views of one object. The picture builds intuition. The matrix lets us compute powers and find the steady state. This picture shows convergence in action. For a 3-state chain, every possible probability distribution is a point inside a triangle whose 3 corners are the pure states, A, B, and C. A corner means you are certainly in that state. The middle means equal chances. Any point inside is some blend. Now scatter several different starting distributions around the triangle. One near corner A, one near B, one right in the center. From each, trace the sequence of distributions as we apply the transition matrix step after step. Watch what happens. No matter where they begin, all the trajectories curve inward and funnel toward the very same point, marked in gold. That point is the steady state, the eigenvector for eigenvalue-one. This is the geometric meaning of forgetting the start. The chain has a single destination, and the starting distribution only affects the path taken, never the place you end up. Different beginnings, one shared equilibrium. Let's make it concrete with weather. 2 states, sunny and rainy. Our transition matrix has columns 0.8 over 0.2 and 0.4 over 0.6. Read the first column. If today is sunny, there's an 80% chance tomorrow stays sunny and 20% it turns rainy. Read the second column. If today is rainy, 40% chance it turns sunny, 60% it stays rainy. Each column sums to 1 as it must. Now suppose today is definitely sunny, so the starting vector is 1, 0. One step, multiply by p to get 0.8, 0.2, an 80-20 split just as the first column promised. Take another step, multiply again, and get 0.72, 0.28. Notice the drift. The probability of sun is sliding down from 1 towards some in-between value, and the probability of rain is climbing. The distribution is visibly converging toward a fixed long-run mix, which will now compute exactly as an eigenvector. Now let's find that long-run mix exactly by solving for the steady state. We want a distribution pi with a sunny share S and a rainy share R that the matrix leaves unchanged, so p times pi equals pi and whose entries sum to 1. Writing out the first equation, 0.8s plus 0.4r equals s. Rearranging, 0.4r equals 0.2s, which simplifies to s equals 2r, so sunny is twice as likely as rainy in the long run. Combine that with s plus r equals 1, 2r plus r is 1, so r is 1/3 and s is 2/3. The steady state is 2/3, 1/3. Let's check it. P times this vector gives 0.8 times 2/3 plus 0.4 times 1/3, which is 2/3 again, unchanged as required. So in the long run, regardless of whether today is sunny or rainy, 2/3 of days are sunny and 1/3 rainy. That single eigenvector is the climate behind the weather. Let's do a 3-state steady state, since the method scales up unchanged. Here is a 3x3 stochastic matrix. You can check each column sums to 1. To find a steady state, we solve p minus the identity times pi equals 0. That is just the eigenvector equation for eigenvalue-one rearranged, together with the requirement that the entries sum to 1. Row reduce p minus the identity, which will have a free variable because 1 is an eigenvalue, then use the normalization to pin down the answer. Working it through gives pi approximately 0.32, 0.44, 0.24. Let's confirm, multiplying p by this vector returns the same vector, so it is genuinely fixed. Reading the result, state 2 carries the largest share, so it is the long-run favorite, the state the system spends the most time in, regardless of where it started. Same recipe as the 2-state case, solve for the eigenvalue-one eigenvector, then normalize so the probabilities sum to 1. For the finale, the most valuable eigenvector in history. Imagine a random surfer browsing the web. At each page, they click one of its outgoing links at random. The states are web pages, and the transition matrix is just the link structure, made column stochastic. PageRank is nothing but the steady state of this chain. A page's rank is the long-run probability that the random surfer is sitting on it. Important pages are the ones the surfer keeps returning to, because many links, themselves from important pages, point in. There is one wrinkle. Dead-end pages with no outbound links and little clusters that trap the surfer can break convergence. Brin and Page's fix was elegant, with probability about 85% follow a real link, and with the remaining 15% teleport to a completely random page. That damping makes the combined matrix stochastic, regular, and strictly positive, which guarantees a single unique steady state. A page's rank is its entry in that one eigenvector, computed across billions of pages. Before the history, it's worth seeing how far this one eigenvector reaches, because Markov chains are everywhere once you recognize them. We already met PageRank and search ranking. A second giant is Markov chain Monte Carlo, a cornerstone of modern statistics and machine learning. The trick there is run in reverse. You design a chain whose steady state is exactly the complicated distribution you want to sample from, then let it run and collect where it goes. In operations research, queues and reliability models use the steady state to find the long-run fraction of time a server or a machine is busy. And Markov chains show up in genetics, in language models, even in board games. Snakes and Ladders is literally a finite Markov chain, and the expected number of moves to finish is a steady-state style computation. The pattern is always the same. Whenever a system hops memorylessly between states, the question of where it spends its time is just one eigenvector away. A little history, and it is a great one. Markov chains were invented by Andrei Markov in 1906, and his first application was charmingly unexpected. He analyzed the sequence of vowels and consonants in Pushkin's poetry, showing that even dependent random events obey clean laws. Right after, between 1907 and 1912, Oscar Perron and Georg Frobenius proved the theorem that underpins everything we did today. A matrix with all positive entries has a unique largest eigenvalue, and its eigenvector can be chosen entirely positive. That is precisely what guarantees a single, well-defined steady state. Then, in 1998, two Stanford graduate students, Sergey Brin and Larry Page, modeled the entire web as a giant Markov chain and ranked pages by the steady state. They called it PageRank, and they founded Google on it. A 19th century idea born from counting letters in poetry now quietly orders the whole internet. Let's recap. A Markov chain is a memoryless system that hops between states, and one step is a single multiplication by the transition matrix P. That matrix is stochastic. Its entries are non-negative and every column sums to 1, so it always sends a probability distribution to another probability distribution. Because the columns sum to 1, the matrix always has eigenvalue 1, and the eigenvector for that eigenvalue normalized to sum to 1 is the steady state pi, the distribution that P leads unchanged. Diagonalization shows why the long run is so clean. Every other eigenvalue has magnitude below 1, so its part decays under repeated powers, and the chain converges to the steady state no matter where it started. And the crown jewel, Google's original PageRank modeled the whole web as one enormous Markov chain and ranked every page by its share of the steady state eigenvector. Next episode, we turn to symmetric matrices and the spectral theorem, where eigenvectors meet at perfect right angles and diagonalization reaches its most beautiful form. Today, we put matrix powers to work on randomness. A Markov chain hops between states, and its rule is captured by a stochastic matrix, a square matrix of probabilities whose columns each sum to 1. Multiplying a probability distribution by this matrix advances it one step. The key fact is that a stochastic matrix always has eigenvalue 1, and its eigenvector, scaled to sum to 1, is the steady state, the distribution the chain settles into and then never leaves. Diagonalization tells us why the long run is so simple. When we write the matrix in terms of its eigenvalues, every eigenvalue other than 1 has magnitude at most, 1, so those parts decay away under repeated multiplication, leaving only the steady state. So for a well-behaved chain, no matter where you start, the distribution converges to that one eigenvector. This is exactly how Google's original PageRank worked, model the whole web as a giant Markov chain of random clicks, and a page's rank is its share of the steady state. Next time, we turn to symmetric matrices and the spectral theorem, where eigenvectors meet at perfect right angles. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.